Hello, welcome to this workshop on momentum and impulse. Let's get right into it. So, momentum deals with collisions, and with collisions, we need to check what was happening before the actual collision took place, how fast cars were traveling if they were cars, and how much their masses are if they are cars or whatever objects that are in question. Then we know that whenever collisions happen, right, momentum is conserved. So we need to take into account the conservation of linear momentum. Then once momentum is conserved, we can represent that by using this formula here, right? The sum of momentum initially is equal to the sum of momentum finally. And this in more detail is m1 vi1 plus m2 vi2 is equal to m1 vf1 plus m2 vf2. That is the formula for conservation of linear momentum. Now there's some stuff that is happening during a collision as well, right? And we need to take into account what? Impulse. And impulse is what? Given by this formula. If net delta P is equal to if net delta T is equal to delta P, that is the change in momentum. That is impulse. Now, linear momentum is given by P, and its SI unit is kilogram meter per second. Momentum is a vector. In our questions, we need to choose a positive direction and a negative direction. Now, impulse, which is F net multiplied by delta T, is also known by this SI unit in Newton second, because force is newtons and time is in seconds. Now, impulse is a vector. It is a force acting over a period of time, and it is equal to the change in momentum in the positive or negative direction. So let's say we are an object here, right? And where are we going? We are going to the left. Let's quickly do that. So this is where we are, and we go to the left. We stop at 4, right? So our momentum here is 8 when we start, and here when we end, our momentum is 4. So the change in momentum there would be the final minus the initial, and that will leave us with minus 4 kilogram meter per second. That is what? The change in momentum. So if we were going to the right, we would have the same thing. Now it just means when we go to the right, we're going to have a positive 4 kilogram meter per second, and this just shows you that here it will be positive because of the direction that side, and that is the impulse. Remember, it's the change in momentum. Now, since linear momentum is conserved, if there are two objects, the momentum gained by one object is equal to the momentum lost by the other object. Remember, this is always a closed system. You cannot have momentum escaping. Due to Newton's third law, the force of A on B is the same as B on A. Since a collision is a contact force, the change in time is also the same for both objects, since A touches B only when B touches A. Thus, the impulse, or F net delta T, is also the same for both objects but opposite directions. Now, let's look at this example here. Object A with mass 200 kg is moving west at 10 meters per second. Object B with mass 100 kg is moving east at 15 meters per second. The objects collide and are in contact for 0.1 seconds. After the collision, object A is moving west at 2 meters per second. Now let's see what they want us to do. They want us to fill up this table there, or complete the table. Let's try to do that. What is the initial momentum of A? We know momentum is mass multiplied by velocity, right? So let's take west as positive, and then we'll take east as negative. Now this just means the initial momentum of A will be 200 multiplied by 10, and that gives us 2000 kilogram meter per second. Right, that's the SI unit for momentum. Then for object B, its initial momentum will be 100 multiplied by 15, but in the opposite direction. So that'll be negative 1500 kgms. Just like that. The negative just tells us about the direction. Now we need to find the final momentum. Now we can easily find the final momentum there by using m1 u1 plus, let me just go back, my slide just went forward, so it's m1 u1 plus m2 u2 is equal to m1 plus m2 moving with one velocity. So u just stands for initial velocity, right? Now we can easily find what velocity they are moving with. So we know that the initial momentum, right? Remember, this is the initial momentum of A. So I'll just say it's 2,000 instead of even doing the calculation again, right? Minus 1,500 for the momentum of B. This is equal to 200 plus 100. The mass is 200 plus 100 with one velocity. Now on the left hand side, we are going to have 500 is equal to 300 V. Then let's quickly find what V is. Then V is equal to 1,7 meters per second. There we go. Now we can find the final momentum of A. How do we do that? We just take 200 multiplied by 1.7. Let's quickly do that on our calculators. So that'll be 200, its mass, multiplied by 1.7. Now this is just going to be 340 kgmas. Now we need to find the final momentum of B, and that is just going to be 100 multiplied by 1.7. That is 170. There we go. Now it's quite easy for us to find the change in momentum. And how do we do that? The change in momentum is equal to the final momentum minus the initial momentum. So let's quickly find that on our calculators. That'll be 340 minus 2,000. Let's quickly do that. And that is 1,660. Let's do the same for object B. 170 minus a negative 1,500. And that is just going to be 1,670. Then what is the impulse? Remember, the impulse is the change in momentum. So it means that the change in momentum is equal to the impulse. So we can just say that's 1,660. Copy those values, put them here. Those are the same thing. Right. Now, what is F net? Remember, F net delta T is equal to the change in momentum. Then we can divide both sides by change in time. Now we can find, so these will cancel, so we can easily find F net by saying the change in momentum over the change in time. So it'll be what? 166, that's supposed to be a 0, right? So 1660 divided by 0,1. Let's do that. 1660 divided by 0.1, and that gives us 16600, 0. Then we need to do the same thing for B, right? So that'll be 1670 divided by 0.1. 1670 divided by 0.1, and that gives us, quickly write that down, 16700, 0. And there you have it. Now let's carry on. So let's look at linear momentum, right? So if we look at this table here, right? So we have velocity versus momentum, right? Let's see how they affect each other, right? Because it's linear momentum, right? As the velocity increases, the momentum would also increase, right? They are directly proportional to each other. Now, with kinetic energy, because as we go to the right there, right, as the velocity increases, right, because there is a squared there, this is how it affects the kinetic energy. So, as the velocity increases there, the kinetic energy also increases, but it's not a linear graph, it's exponential. Now let's look at this example. A truck is moving with a velocity v and kinetic energy of k. The velocity is now tripled. What is the new kinetic energy of the truck in terms of k? Let's see what we can do there. They didn't give us any units, but we should still be on the right track. Let's see. Truck is moving with a velocity of v and kinetic energy of k. So let's look at the kinetic energy. Ek is equal to half mv squared. Now we know that its kinetic energy is k. Now they're saying if the velocity is now tripled, so let's see what would happen if the kinetic energy, if the velocity is tripled. So this will be a new kinetic energy. A half, the mass is still the same, the velocity is now tripled. Tripled just means 3 times v, and we need to square this. So this means we have half m9v squared. So we can just start with the 9 and say this is 9 into 1 over 2 mv squared. Right. Now, as you can see, this guy here is the same as that one there. But now there is a 9 in front. So what happened? Right? So it means that it was multiplied by 9. So in terms of k, it's just going to be 9k. Let's carry on. Now let's look at inelastic and elastic collisions. So in elastic collisions, kinetic energy is conserved. Right? No. Now this just means the kinetic energy initially is equal to the kinetic energy after. So the sum of those energies initially will be equal to the sum of those energies after the collision. Now we can just add the kinetic energy of the first object plus the second object before the collision plus the kinetic energy of the first object plus the second object after the collision. Those must be equal to each other. Now in inelastic collisions, kinetic energy is not conserved. Now, this just means the sum of kinetic energy initially is not equal to the sum of kinetic energy after or finally. Now, let's look at bouncing objects. Right, so if it's elastic, this is how you'll have the velocity versus time graph. Remember, the kinetic energy is the same, so we cannot lose any velocity there, right? So if we try to draw a straight line there, you'll see that all these points line up because nothing is lost, right? That's a velocity versus time graph there. Now, this would be its displacement versus time. Because nothing is lost, if it bounces to this point, even in the second bounce, it'll come back to the same point. Nothing is lost. Everything is conserved. So that's just the displacement time graph of a bouncing object when the collision is elastic. Now, if the collision is inelastic, this is what you would have. So the velocity decreases every single time. If you try to draw a straight line there, you'll see that it actually decreases. Every single time it decreases because now we are losing some energy. Kinetic energy is not conserved. Then let's look at its displacement versus time graph. That's what it would look like because we're losing energy. So the velocity becomes smaller and smaller. So if the velocity is smaller, the less distance traveled after every single bounce. Now let's look at F net and impulse. So the formula is just F net multiplied by time is equal to the change in momentum or the impulse, right? So if we try to solve for F net, we will have the change in momentum over the change in time. So F net is the rate of change of momentum. This is an alternative way of stating Newton's second law. F net is equal to ma. Now let's look at impulse from a graph, right? So as time goes to the right like that, the F net increases, right, until a certain point where it now just comes down like that, right? Now let's see, right? So it just means as we increase time, right, eventually we're going to make F net smaller, right? Remember, we have this F net is equal to change in P over the change in time. So as we increase the time, what are we doing to F net? We're decreasing it because they are inversely proportional. Now this is why, let's look at impulse and safety systems. This is why we use airbags in our cars. Whenever an accident happens, the airbag comes, right? Why does the airbag come? It increases the contact time, therefore the net force is going to be less, and then the chances of you getting hurt are less. And also the crumple zone in front of a car, right? It increases the contact time and it reduces the chance of injury. Whenever you jump, you should also bend your knees, which increases your contact time and making you less prone to injury. Now it's your chance to pause and try the following question. Okay, now that you've paused the video and attempted the question, let's see if you're on the right track. A, they said determine the velocity of the SUV immediately after the collision. Now remember this, the cars did not stick together, right? So this means we can use the conservation of momentum, but now we can just say M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. The U just means initial velocity. So instead of writing VI, you can instead use U. Then let's substitute. So we have 1084 times the velocity initial, which is 33, plus the mass of the SUV, which is 3437, multiplied by its velocity, but it's moving in the opposite direction, so it'll be negative 28. Then we have the mass of the car still being 1084, then its velocity is 5, but waste, so that'll be minus 5 there. Then plus the mass of the SUV, 3437, and we want to find its velocity. So now let's quickly solve for V2 there. Let me just put that 2 to show that it's the second object. Now let's quickly check what this guy gives us there. On our calculators, we can quickly say 1084 multiplied by 33, and that gives us 35772. So 35772. Then this will be minus, let's check that on our calculator as well, 3437 times 28, and that is just 96236. And this is equal to, let's check that on our calculator, is 1084 times 5, and that is minus 5420 plus 3437 V2. And let's solve that there. Now we know that can just say 35772 minus 96236 plus 5420, which just gives us minus 55044 is equal to, remember there's a negative there, 3437 437 v2. Then let's divide both sides by 3437. 3437. Then v is going to be equal to 16 meters per second. In which direction? To the right. Why? Because the answer that we found there was negative. Now let's go to the next one. Now they're saying the contact time of the collision was 0.2 seconds. Determine the net force experienced by the car. Right. Remember, if net is equal to the change in momentum over the change in time, then the change in momentum, we can say it's the final momentum 5420 minus the initial momentum, which is 35772. This will be over the change in time, which is 0.2 seconds. And let's check, that is just negative 41192 over 0.2. Then let's check on our calculators. And that gives us negative 205,960 newtons, right? And this is a very big force because it bumped into a car with a very big momentum. So it bumped into this one and it even changed direction. So you expect this to be quite big. Now let's carry on. Then they're saying determine whether the collision is elastic or inelastic by use of an equation. So first, let's find the kinetic energy before, right, before the collision. So we know, I'll just say EK before is equal to half m1 u1 squared plus half m2 u2 squared. So it's quite easy. Now we just substitute 1 over 2, the mass of the car 1084, then the velocity was 33, we need to square that, plus 1 over 2, the mass is 3437, and then the velocity is 28 but in the opposite direction, but it wouldn't matter that much because we are going to end up squaring it. Now we just rely on our calculator to find what that is. Let's quickly do that. And that gives us 1937,542. That is the kinetic energy before. Now we need to calculate the kinetic energy after. Let's quickly do that. So for after, let me just draw a line there so that we don't end up mixing the two. Then we'll use the same formula, but we'll use V. So V, remember, it stands for final velocity. So I can just say this is equal to half 1084. The final velocity of the car was 5, but in the opposite direction, but that doesn't matter because we're going to end up squaring it, plus a half 3437, and then the velocity of the SUV was minus 16, but it doesn't matter because we're going to square it. Now let's check if we're going to get the same answer as above. So 0.5 times 1084 times 25, and then plus and that gives us 4, 5, 3, 4, 8, 6, 0, and therefore the collision was inelastic. Because the kinetic energy before is not equal to the kinetic energy after. Now let's carry on. Right. D says the fireman at the scene of the collision tells you the vehicles are crumpled up because modern vehicles are made cheaply. Is he right? Explain. No, he isn't right, because modern cars are fitted with crumple zones. Why? So that they can decrease the contact time. And remember, we know that F net is equal to the change in momentum over the change in time. Now, if they increase the contact time when they crumple, this means the forces will be less. So he isn't right, because these cars are made to crumple so that the forces on the people is less and to reduce the chance of injury. Now, why should people wear seat belts? Refer to a law of physics in your answer. So remember, during a car collision, there is no unbalanced force on the person. So according to Newton's first law, the person will continue to move at the same speed. The main purpose of a seatbelt is to bring an unbalanced force to the person by stopping the person from moving out of the car. I hope you enjoyed this workshop on momentum.